So we are still in chapter 1, and this is the second part of chapter 1 where we're going to talk about measurements, okay, and what is meant by this whole thing. Let me take you back to the previous section for just a minute, and we talked about the scientific method, okay, back there we talked about observation, hypothesis, experimentation, theory, and law. And this is how we actually do any kind of scientific research. So I want to bring your attention to experimentation, which I've highlighted over here. This is the biggest part of any kind of scientific work, all right? Any kind of science work that you do, this is what we mean when we say something is fact-based, that you've collected data. And this is a part of experimentation. So, which means that if you're collecting data, then your data should be good. If your data is not collected well, then your experimentation is wrong, then your hypothesis is wrong, then you will not be able to conclude a theory from it. So which means your experimentation has to be good, which means your data collection has to be good. So how do you know what data to collect, how it is measured, and then of course, is it valid or not? Is it accurate or not? Is it good data? You don't want to publish anything that is not good data. It will not be published anyway, or it will be rescinded later on. So you want to make sure that you have good data. All right, so this is all part of the experimentation part of the scientific method. So here are the things that we actually measure. So if I say to you that I am 45, in your mind your first thought would be, oh, age. Okay, so it must be 45 years old. But maybe actually I'm trying to say that I weigh 45 kilograms, okay, or something like that. So the units become really important for us, okay, as to how do you define that number. We can just not use a number randomly and say, okay, this is 10 or this is 12. You cannot just say that. You have to actually signify what is being measured by a unit, okay. There are two kinds of units that we use. One is a non-SI unit and one is an SI unit. SI unit are the standard units that are used by the entire world. The non-SI units are the non-standard units, which is used by, yes, you guessed right, USA. Okay, so we still use the non-SI units, whereas the entire world is using the SI units. So, which means that we have to learn conversions also, okay, but we'll get there in a few minutes. But first of all, let me talk about all the quantities that you can actually measure. So for example, when you measure length, you measure that in miles, feet, inches, and so on. The SI unit for that is actually meters, all right? And we will talk about centimeters and all that later on, because I know you're probably thinking, we can measure in centimeters, but we can, yes, of course. So we'll talk about that in a few minutes. And then we have weight. Weight can be measured in pounds and ounces. And more also. Okay, I'm not writing all of them over here, but I know you probably know that this could be a weight unit. The SI unit for weight is grams. For time, it's seconds. And thank God the SI and the non-SI for this one is still the same. Okay, they're both seconds. You can also measure temperature. Temperature is measured in Fahrenheit or Celsius. The entire world uses Celsius. We use Fahrenheit in USA. And then the SI unit for temperature is Kelvin actually. And Kelvin is used only for calculations. For example, it's used only in chemistry and physics when we're doing calculations. Otherwise, colloquially and whenever you're talking to somebody, it's going to be Fahrenheit or Celsius. Then you can also measure electric current, which is an ampere. And volume is measured in gallons or quarts or pints. The SI unit for that is liters. And then we also have pressure, which is atmospheres, torr, Pascal. The SI unit is Newton, okay, and also in some cases Pascals. But anyhow, these are the physical quantities that we will be working with, not so much ampere. Maybe in Gen Chem 2 you'll work a little bit with ampere, but all the other quantities we'll be working with this in Gen Chem 1 also, all right? So you'll get an idea of how they're used. So now that we're doing measurement and we know the units, we now have to talk about what we use to measure these things. So for example, for a length, you would use a meter stick or a measuring tape. And that measuring tape would have units in centimeters or inches. Time would be measured by a watch or a stopwatch. Solid volume can be measured by a meter stick, because remember, for solid volume, you still have to figure out the units in meters or centimeters, okay? But for liquid volume, things are a little bit different, and so you would need like a measuring cylinder or a beaker. Temperature is measured by a thermometer, and weight is measured by a balance or analytical balance, and then pressure is measured by a barometer. Now, not all of the measurements are listed over here, so there might be some other instruments that you will use. However, these are some of the most common instruments that you will use in the chemistry lab, and you'll be measuring length and time, and definitely liquid volume and temperature. Weight, absolutely, you will start using that from the first week also. All right, so these are the instruments you use for measurement. Now I want to bring your attention a little bit to the non-SI units and the SI units, and what is the difference between the two, and why we actually use SI units everywhere, and why non-SI units are a little bit confusing. Okay, so first of all, let's talk about which unit is larger. So we have pint or gallon. Okay, so there are two units for measuring volume. Which one is larger? Take a guess, educated guess. If you said gallon, you're right. Okay, 1 gallon is equal to 4 pints. So gallon is the bigger unit. However, you may not know this if you were not familiar with the gallon or the pint. Inch or foot? And you're right again. You probably chose foot. Okay, foot is the bigger unit because in 1 foot we actually have 12 inches. All right, so that makes a foot a bigger unit. So again, any person who's never heard of a foot or a feet before or inches before, they would not know this. All right, so for example, if you were to figure out how many inches there are in a mile, you probably would have to think about that a little bit. All right, foot was easy conversion, but in a mile, it may not be also easy. And finally, score or a decade. I'll let you think about that one, okay, and see which one is the larger unit over here. So this means there are some issues with the SI units, okay, or with the non-SI units, excuse me, and that's why we actually went to the SI units, because it gives us a little bit better framework to work with, and so everybody is on the same page. So here are the SI units, all right, and if you look at the SI units here, it's a very systematic kind of a thing, all right? So for example, each of the unit has a prefix. What you will not see over here, okay, in all of this, don't look at the examples yet. If you look at all of this, you don't see the unit that you're measuring. So for example, you don't know whether you're measuring liters or meters or kilograms or grams or temperature. What are you measuring? You don't know, all right? So which means that there is some standard things regarding the size of the unit, all right? So there are the prefixes in the first column that we have: tera, giga, mega, kilo, deci, centi, milli, micro, nano, and pico. Okay, this is how much we use so far. And these are the symbols that go with it. And this is very standard. Whether you're trying to measure liters or grams, you would still use the same kind of a prefix. Okay, and then here are what it really means as far as the quantity is concerned, all right? So here right in the middle, we have what is called the base unit, all right? Right here between 10 to the power of 3 and 10 to the negative 1. Now 10 to the negative 1 means 1 over 10, okay? So 0.1, 10 to the power 3 means 1000. So that's over here, so which means this is the bigger unit, this is a smaller unit. So in between these two, I'm going to go ahead and put my base unit. And my base unit means that I have something here without any kind of a prefix. So for example, liters, meters, seconds. This is without any prefix at all. If I were to measure weight, I would put grams also over here. Okay, so which means that if I have to go to a larger unit, I would go ahead and put K in front of it. K stands for kilogram. So for example, my meter will turn into kilometer, or it can turn into a megameter or gigameter, all right? On the other hand, if I was going to a smaller unit, my meter would turn into a centimeter, a millimeter, a micrometer. The same thing can happen with liters, all right? Liters is a volume unit. So if I go to a higher unit, I can have kiloliters, or I can have megaliters, or if I'm going to a smaller unit, I can have a centiliter, a milliliter, a microliter, and so on and so forth. Now the micro and the milli, okay, and mega, they all have the same meaning. It's not like the inches and the feet, because when we have inches, there were 12 inches in 1 foot and 4 pints in 1 gallon, which means that your conversion units are also not standard. In one case, you're using 4, in one case, you're using 12. So even that is not standard. However, in SI units, everything is based on tens. So if you can look over here, and look at the tens, all that is changing is the number of zeros. Okay, that's all that is changing. So which means it becomes really easy for us to remember. Instead of trying to remember whether there are 12 or 4 or 36 and something, all we need to remember is how many zeros we have in something. Okay, and so your larger units actually go to the top and your smaller units go to the bottom. Okay, so which means that deci, centi, milli, all of that is going to be smaller than the base unit, and then the kilo, mega, and all those are going to be larger than the base unit. Anything that is larger than the base unit, you can see that it actually has a positive number, 10 to the power of 12, 9, 6, and 3. These are all positive numbers. These are all large numbers. Anything going below the base unit has a negative exponent, and negative meaning that it is a small number. Okay, so which means 1 over 10, 1 over 100, 1 over 1000. So it makes it small. Now here are some of the examples that that might help you a little bit. And what is nice over here is you can also see some conversions. Okay, so for example, in 1 kilometer, there are 10 to the power of 3 meters. That's the 1000. Okay, and remember meters was right here as a base unit. Okay, so when you talk about a kilometer, it must have more meters in it. When you go to the smaller unit, okay, so for example, when you talk about millimeter, then it's going to have a smaller number of meters in it, okay, because meters is the base unit and millimeter is a smaller unit. So 1 millimeter actually has 1 times 10 to the negative 3 meters, okay, or 1 over 1000 meter. That's how it is. All right, so these are the smaller units and these are the larger units. We're going to do some conversions later on and you will see how to go from one to the other. Now, one of the things that I need to tell you over here so that it doesn't slip by me is that you have to know these SI units. Okay, I don't expect you to remember the non-SI units, but I expect you to remember the SI units. And I need you to remember from mega all the way down to nano. Okay, deci is not used that much, so you probably will not see too many problems with this, but kilo, mega, giga, this is used a lot, and definitely up till mega. And then centi, milli, micro, nano, these are used a lot. Pico is not used so a lot. So which means if I give you something for pico and tera, for example, it would be as a homework, so you can look in your textbook, okay? But for the other ones, you must know all the prefixes and you must know what the quantities are that go with it, okay? So these are your SI units, very standard. Before we go too far, I just want to go over scientific notation with you in case you haven't done this before. And please get comfortable with this because we're going to be using this quite a lot. All right. So a scientific notation is when you represent something in terms of 10 to the power of something. So you have a number times 10 to the power of n. N can be positive or negative, whatever it is. Okay. But it's a number. A here is a very specific number. Specific number meaning it should be greater than 1 and less than 10. If it is more than 10, then the 10 has to be moved into this 10 to the power of something. So if it is more than 10, then it's going to be one more number here. If it is less than 1, then it will be one less number over here. So if that is confusing you, then you can forget about that. But in any case, A should be less than, more than 1 and less than 10. Okay, that's what it should be. And the whole point of writing scientific notation is to make sure that your numbers are significant. Okay, so this is really one of the key things in converting an insignificant number to a significant number. Large numbers to a smaller number and a small number to a better number, okay, which means something to an accurate number, a significant number. So A should be significant, okay, that's the whole point of doing this exercise. So in scientific notations, you can have numbers that are very huge numbers that you may not want to write the number of zeros off, and then you can have very small numbers also, okay, and they can all be expressed in 10 to the power of something. So for example, Let's look at some of these, okay, over here. Now, if you have this number, it tells you right away that you have a small number because you have a decimal space on the left-hand side, okay. Now, this decimal spot has to be moved to the right when you're converting this into a scientific notation. Remember, the number A here has to be between 1 and 10, which means that I have to have 6.53. Okay, now because this number is less than 1, definitely much smaller than 1, which means that my 10 to the power of n here is going to be a negative number. Okay, because technically this is a very small number, so it has to be negative. Okay, and so this is then going to be, you'll move the decimal point 1, 2, 3, 4. So once you bring it to the right side, it will be negative 4. Okay, so that's what the first number is. Okay, 6.53 times 10 to the negative 4. The next number here is a huge number. It's a large number. The zeros are on the right hand side. So if it's a large number, that means that your n number is going to be positive. Your first number A still has to be between 1 and 10, so which means 3.5. Okay, so we're going to take 3.5 over here, so which means that my decimal point, which really is not visible over here, but it's right here. Okay, so if it's not visible, it means it's after the last number. So if it's over here, then you go 1, 2, 3, 4, 5. So it's 3.5 times 10 to the power of 5. That's what this number will be if written in scientific notation. And then this number here, 0.02700, this one is less than 1. Okay, these zeros are not going to be important for us because the key thing is coming down right here, okay, to 2.7. That's the important thing. But because these zeros are written over here, we're going to go ahead and keep them. Okay, we didn't keep these zeros, but we'll keep these zeros. And I'll talk about this when we get to significant figures, all right? So we'll keep these zeros. And so then we have 2.700, 2.700. Then we just have to move the decimal place and see what number we need on the top, okay, for the n number. So 1, 2. Okay, and since we move to the right, it's going to be negative 2. So when you move the decimal place to the right, it's going to be negative. If you move to the left, it's going to be a positive number. So these are scientific notations, and please get comfortable, okay, with the scientific notations. Now using the units with scientific notations, because if you go back to the previous slide and look at the SI units, you notice that we went from the base unit to kilo to mega, which is 10 to the power of 6, and then micro, which is 10 to the negative 6. So which means that we have to deal with these scientific notations all the time. All right. So which means that we should be able to go from one to the other. The other thing I also mentioned to you back there was that you need to know the conversion of all of these things. Okay. And so you should be able to do this without looking at the table with just your mind. Okay. And so here we have 4.851 times 10 to the negative 9 gram. Okay. What is the approximate SI prefix for this one? Now for looking for the SI prefix, what you're looking for is this number, okay, on the 10 to the power of whatever, because that's the nice thing about the SI units, everything is based on 10, okay, so 10 to the negative 9 is actually nano, okay, which is a small thing, and remember this is negative 9, which means that it is a small unit, okay, so now this becomes 4.851 nanogram. 3.16 times 10 to the negative 2. So negative again means we're looking at something that is smaller, all right? And this is in meters. So then 10 to the negative 2 meaning 1 divided by 100. And that is a centi, okay? 100 is a centi. So which means this one is 3.16 centimeters, okay? And then this last one here, 8.93 10 to the negative 12. Again, negative 12 is a given unit in that table. And negative 12 is pico. Okay, and so which means that this is 8.93 picoseconds. What does this really mean for us? Okay, what does this mean? You can look at it in a reverse manner also. Okay, what this means is that if you have 4.81 nanograms, that is actually equal to 4.851 times 10 to the negative 9 grams. So if you had to go from nanograms to grams, it would be times 10 to the negative 9, okay, grams. That's what it would become, because in grams it would be a very small number, because nanogram is a very small number, okay. And similarly over here, 3.16 centimeter, in meter case it would be a very small number because centimeters are smaller than meters, okay. I hope you're getting that aspect of a ratio over here, okay, of what is a small unit and what is a larger unit. So here are some more examples. Okay, so if you have 6.20 kilometers and you convert that to meter, okay, now kilo is a larger unit. So if you're going to meter, you will have to multiply that by 10 to the power of 3 because kilo is 10 to the power of 3. Okay, that's how it will be. So it's an easy conversion, and it's a nice thing because again, you're just working with zeros. Okay, you're not working with any other number. So all you have to do is put the exponent there. Going from centimeter to meter, again, centimeter is a smaller unit, meter is a larger unit, which means that you will have to add the exponent 10 to the negative 2, okay? And 1.98 nanoseconds to seconds. Now, nanoseconds is a small unit, seconds is a larger unit. So, which means that your exponent is going to be a negative number, okay? So, if you had a larger unit going to a smaller unit, it would be a positive number. Going from a smaller unit to a larger unit, you would have a negative number. Again, large unit to small unit, positive. Small unit to large unit, it would be a negative number. Now for measurement again, we've talked about how to measure things and what are the units. There are two other things that need to go with measurement, and that is whether it is precise or accurate. Precision means that the values are actually close to each other, and accuracy means that it is actually close to what the value should be, okay, which means the actual value. So for example, if you're trying to measure something, if you're trying to throw something in this basket, if it goes into the basket every single time, then your aim is both accurate and it is precise. Okay. Now, if you're trying to throw in the basket, but every time you aim, it goes outside the basket, it is not accurate because it's not going in the basket. But it is precise because it keeps doing the same measurement over and over again, or you keep aiming at the same place again and again. Now, if you're like me, okay, then you're trying to throw something in the basket, then here we have all over the place, okay, which means that my data here or my aim here is neither accurate nor precise, okay, because I can't seem to get anything right over here, which means that my instrumentation is not correct actually, all right? And so when you do measurement, it is good to have accuracy. That's definitely true, okay? You need to have the actual measurement close to the actual value. Precision is also good in some cases because in some cases you can get away with a precise value, all right? Because in some cases you're working with subtractions, and so that is how you will figure out the actual value. But if it's neither accurate nor precise, then your data is pretty much useless, okay? Which means that your instrument is ready to be thrown in this wastebasket, okay? And you need to get a new instrument. One other aspect about collecting data is significant figures, which means that is your data significant or not, all right? Or which one is a better data? So for example, if you look at these two numbers, 5.12 grams and 5.124 grams. So which one is more significant? Which one is a better data? And yes, you're all saying 5.124 grams is better. Why? Because it has one more number, okay, than the 5.12. So obviously this is a lot more accurate. And this accuracy actually depends on your instrumentation. If your instrument is good, then you will have good data. If your instrument is not going to measure until the third decimal place, then it's not going to be good data, all right? So it depends on what kind of instrument you're using. The way we define significant figures is those digits in a measurement, measured number that include all certain digits meaning whatever is measurable, plus a final digit having some uncertainty. Okay, so which means that you must be able to read at least one number, and then you will have one number more which will be sort of uncertain, okay, not quite readable. So for example, let's look at this ruler, all right? This is in centimeters, and remember, this is within centimeter, you can have millimeter, all right? 10 millimeters make up to 1 centimeter. Looking at this ruler right now, you have a measurement of 0.5 centimeters. So this is 0.5 centimeters. This is 1 centimeter. This is 1.5 centimeters. This is 2 centimeters. Between here, these are millimeters, except that the gradient is not given to you. And if it's not given to you, you cannot measure it. Okay. So if we are trying to measure this nail, we know that we can measure up to 5 without any problems at all because we know that this is 5. We cannot measure up to 6 because the nail does not reach up to 6. Okay, so we have to stop at 5. So which means we have 5 point something because we know it's more than 5. Now, if this nail had stopped right here on this line, then it would be 5.5, but it is a little bit more, okay, than 5.5. So now it's kind of in between somewhere. So now you have to guess this number, and that is the uncertainty that we're talking about. So this number becomes 5.7. If you had chosen 5.6, that would be okay. If you had chosen 5.8, that is fine also. And that is why it is an uncertain number, because as anyone is looking at these things, when they're measuring, not everyone is going to look at the same thing. So that is why it is uncertain, all right? And that is allowed, but only one digit, okay? So for example, you cannot say that this is going to be 5.75. That would be wrong, okay? Because you cannot go to the second decimal place because that is not given to you for measurement at all. Even this number, the 7 over here, is actually insignificant, all right? But you're going to put it in a significant figures because there is some uncertainty, and there is, you know that it's going to be around there somewhere, okay? But you know for sure 5 is a measured number. So usually there is going to be one certain digit plus one digit with one some uncertainty. This is how you will have to measure in your lab also, by the way, okay? For everything, whether you're measuring length or volume, okay? For weight, it's going to be a little bit easier because your weight has definite numbers in it, but because it's a digital balance. But for volume, you're going to have some degree of uncertainty in it, okay? So that's what we call significant figures. So now that you know about the significant figures as to what it is, it's a measured quantity. We need to understand how to work with significant figures, because once you start collecting data, not all your instruments are going to have the same degree of accuracy. And so in one case, maybe you have a measurement which gives you more significant figures than the other one. So you need to figure out how to actually work those two out. Okay, and that's a very common kind of a problem that you face in a lab. All right, so for example, you're trying to calculate area, okay, of something. And this is what you come up with in measurements, 1.2356 meters and then 1.95 meters. You have to multiply these two. So then you have to figure out, okay, what am I supposed to do? Okay, how am I supposed to get the answer? Should I have this significant figure or this significant figures? Okay, now the number of significant figures that you have in this one is different than what you have here, okay, because your measurement instrument was different. So the first thing you have to be able to figure out is how many significant figures you have. Then we'll work with the calculation part, okay? And so to figure out how many significant figures you have, here are the guidelines, okay, to do this. So first of all, if you have any non-zero digit, which means 1 through 9, then those are all going to be significant. So for example, 1.95, that is 3 significant figures. 1.2356, this is just count how many numbers you have, which is 5 significant figures. If you have any zeros between non-zero digits, they're going to be significant. So for example, 101. So this zero then becomes significant. Now, if you have any non-zero digits, then it's not a problem at all, because all you have to do is count the numbers, all right? And you will get the significant figures that you have. The problem sometimes arises when you have zeros and then you don't know whether to count that zero or not. So the next few guidelines here are only for zeros, okay? And so here, if you have a zero in the middle, then you definitely have to count it, okay? Zeros to the left of the first non-zero digit are not significant. So if you don't understand the sentence, don't worry about it. But right here, okay, this is what it means. So if you have this zero, this is not significant. The zero after the number is going to be significant. Okay, so this is significant, not this one. If you have zeros that are on the right, and if there is a decimal place present, then you have all the zeros that are significant. Okay, which means that because of this decimal place, these two become significant. Because of this decimal place, these two become significant, which means the total number of significant figures you have in this number is 5. Okay. Now, zeros to the right of a last non-zero digit are not significant if a decimal place is not present. So, for example, when you have 100, 100 is one significant figure. These two zeros are not going to be significant. There are only few cases where these two zeros are going to be significant, and that depends on your measurement. So, for example, if you say that you have 100 pencils, then the 100 is 3 significant figures. Why so? Because your pencil that you have is either a whole pencil or no pencil, okay, which means there is nothing like half a pencil, like eggs, okay, or like erasers. You have either a complete one or none of it, okay. So which means that you have 3 significant figures only if you have a measured quantity. All right, so if you're saying that you have 100 nails, then it is a 3 significant figures. If you're saying you have about 100 meters, then this is 1 significant figure. So you have to decide when this number is exact and when this number is vague. So that depends on the quantity that's given to you. Okay, so let's go over this again. If you have zeros between numbers, that's significant, and zeros before any kind of a number is not significant. After it, yes. And number 3 and number 5 are kind of similar. Okay, so you have to see whether you have a decimal place or not. Okay, and then count that number, that zero, as significant or not. If you have decimal places and then you're counting the zeros, then definitely yes. Okay, it is going to be significant. And then, of course, if you have a whole number like this, like tens, hundreds, thousands, then you have to see and determine whether that number is going to be significant or not. So whether it is 2, 3, 4, that depends on the measurement. So let's do some examples over here. Okay, so we get an idea of how this works. So here is 310.0 grams. So this one here, these two zeros, significant or not? Yes, significant. Okay, because this is a decimal point, so which means that this zero is significant and this one is significant. So that is 4 significant figures. In this huge number, we have 2 different kinds of zeros. One zero is here before the decimal space, and then there is 2 zeros after the decimal point. And so the zero before the decimal is what we consider to be cosmetic zero, which means it's not really required. All right, and so these 2 zeros, however, are after the decimal point, and therefore they are significant. Therefore, the total number of significant figures here are 2, 2, and 2, so that means 6. Okay, so there are 6 significant figures for this number. Again, in this one, we have 3 different kinds of zeros. One before decimal, one before after the decimal, and one after the number and decimal. The one after the decimal and number is significant. The one before the number and after the decimal is not significant, and neither is this zero. We talked about this one already, but this zero here before the 5 is also not significant, but after the 3 is significant. So which means that we have 4 significant figures over here. Please remember, this is all very critical, because once you start doing calculations, you will have to come up with the right significant answer, okay, eventually. So you need to know how to figure out what significant figures you have. In case of D, okay, you have no zeros before the 4, but you have a 0 after the decimal point, okay, and so this 0 will count, which means that we have 4 significant figures, okay, in this case. This exponent number, it does not count at all, okay, so don't worry about exponents when you're asked for significant figures. E is 4 significant figures, and then F is going to be 2 significant figures, because here we are not given any decimal point, and we are also not given as to what this kind of a measurement is. If we were told that this is the number of eggs or the number of stars, then we might say that this is 5. But because there is no measurement given to us, we're going to go ahead with 2. Okay, so these 3 zeros are insignificant. It doesn't change the number value though, okay, which means this is still 91,000. It's just that it is a significance of only 2 figures. Okay, that's all that it matters. Now, for calculations in significant figures, that's how we got started, is if you have 2 different kind of measurements, where you have 5 significant figures in one measurement and 3 in the other one, then how do you actually do this kind of a calculation, and how many significant figures do you end up with? So in case of multiplication and division, you find the lowest sig fig that you have and round off to that number. Okay, so for example, let's look at these numbers here. So you're dividing 6.8914 by these 2 numbers over here. So when you look at this calculation, first of all, it is all multiplication and division. There is no addition and subtraction. Okay, so which means all of it is one kind. So if you have these 3, you need to figure out first which one is your lowest significant figure. So right here, 7.28, this is your lowest significant figures of 3. And that is how you're going to round it off. So once you do the calculation, and this is what your calculator gives you, then you should round off to 3 significant figures. Regarding the rounding off, I've given you some explanation over here, but this is how you would do it. Okay, so if you have to round off to 3 significant figures, you will start from the left. 1, 2, 3. You will look at this, and then you will look at the next digit. And if it is 5 or more, you will round off to +1 to 4. If it is 4 or less, then you will drop the entire number over here. Okay, don't try and round off from 9 to 4 to 8 and then make this one 4 and so on. Don't do that, okay? Just take the three numbers that you need, and then if this is 5 or more, then you make it 7.35, but because this is 3, we're going to drop everything off here. Okay, so the final answer then becomes 0.734. If you're doing addition or subtraction, then you have to find the lowest decimal point, okay, and round off to that number. So which means you're not looking at the total significant figures, you're looking at the decimal points. So here we have 3 decimal points, and here we have 2 decimal points. So which means that by the time you do your calculation and come up with this huge number, you will eventually have to round off to 2 decimal points, not to 2 or 3 significant figures, but the decimal points. So here now, we have these 2 decimal points, 1, 3. So now I will look at the next number over, which is 7, and 7 is of course more than 5. So I'm going to carry that over to the previous number to +1. And so I have negative 1.14 as my final answer. Okay, and so this is addition and subtraction. Multiplication, division, lowest significant figure. Addition, subtraction, lowest decimal number. That is how you will do calculations in significant figures. And here's a little explanation for the rounding off. You can read it. So in this little portion, you need to know the units of measurement, the different kinds that there are, the length, weight, and so on, the SI and the non-SI units. With the SI units, you need to remember the conversions. For the non-SI, I'm going to give you those conversions. You just need to know how to set it up. The terms, accuracy and precision, and of course, how to do significant figures.